Yeah.
If you want the figure, you can attach it from the machine to your.
No, it's fine.
And so the next speaker is Varun. We'll be talking about polynomial factorization. Go ahead.
Thank you. Okay, thank you all for coming. So this talk will be a be an extremely brief introduction to multivariate polynomial factorization. And so there is some new work that I did with Ramanathan and Mrinal that I'll mention in the end. So if you were eagerly waiting for that, then we can discuss it later. But for now, we'll mostly just go over the main sort of template, the ideas that go into factorizing multivariate polynomials. And in the end, I tell you what can you do if you want to try anti-randomness. So this is sort of the brief overview. So what is polynomial factorization? This is just you are given some polynomial f, the multivariate polynomial over some field, and you want to just factorize it into its irreducible components. And just there's some basic so there's some algebra that goes into this. You need to ensure that whatever domain you are working over, like you need to ensure that things like factorization make sense. Can you uniquely factorize things and so on?
So how are you given this polynomial? We what form?
So that's going to be important. So one thing is that you can have just a monomial representation, which when it's univariate, if it's degree d, you have some d terms. Then it's not a problem. But once you have some multivariate setting, then if you have n variables and if you have degree d, then if the way you're representing your polynomials is in this monomial expansion thing, then you can have like n plus d choose d sort of terms, and this is huge. So that will be called the dense representation. But what we'll care about is when you're given some more compact representation for your polynomial, we'll come to that. So yeah, and basically the underlying field will be important. The simplest sort of examples are if you have something like x squared plus 1, over real numbers you can't factorize this, but over complexes x plus I. So why is polynomial factorization? Why is it important? Well, it is a natural question. Polynomials show up everywhere, and factorization, integer factorization is something people have been studying for a long time. Polynomial factorization turns out to be something where we've made much more progress, and we don't expect to make too much progress for integers. And plus, there are many applications. So a lot of applications, pseudo randomness, in hardness versus randomness, where you can where it's sort of like if you can show that there are hard functions, then you can de-randomize things. These sort of statements in the algebraic world, they use polynomial factorization results. Then error correcting codes and polynomial identity testing. Just given a polynomial, you have black box access, let's say, and you want to figure out if this is identically the zero polynomial. And all these settings, polynomial factorization shows up. So before we go to multivariate, just a brief look at what happens in the univariate case, which is simpler. So when you're working over a finite field, so some of the classic algorithms that are known are, one is by Cantor-Zassenhaus, and that is a randomized algorithm, and it's the polytime algorithm. And there's an algorithm by Berlekamp, which is deterministic, but it's slower in the sense, so there's going to be a dependence on the size of the field. And for Cantor-Zassenhaus, the dependence is log of p, whereas in Berlekamp, the dependence turns out to be over in p. So it's poly in p, in r, and in n, and so on. And it's still open to get that for univariate case, deterministic algorithm where the dependence on the field size is logarithmic, we still don't know how to do. okay, over integers or rational numbers. So this is a classic work of Lenstra and Loas, and this uses basically trying to find an approximation of like shortest vector problem in lattices, and using that you can figure out a factorization. And if you start talking about real numbers or complex numbers, so then it starts becoming a matter of numerical algorithms, because your coefficients can have infinite representation. How are you going to represent them and so on? And I just written Abel-Ruffini theorem. All I'm saying is, so for quintics and above, we don't even expect to have an efficient way algorithm for factorizing things, because then it means you can sort of get a formula for the roots of a complex polynomial, we can't have that. So Mrinal is teaching a course on algebra, number theory computation.
So at least if you get it correct, I mean, in the sense of this only means that you have an algebraic form, right? So you can't have the algebraic closed form formula for.
You can't have any closed form.
But this is like the is that I mean, one implies other.
No, so
I mean,
can you numerically do some? No. So these are those numerical algorithms. So I don't know much about them, but so for example, even over real numbers, you can do things like Newton iteration and things to find roots. So there, I guess things are fine. You can. I don't know how strong your guarantees can be. Like, can you? Are there statements of the form that you cannot hope to get a deterministic algorithm that factorizes real numbers? Like again, representation is a problem, but even if you're allowed to, if you're somehow told you can store real numbers and you can do unit operations and so on, I am not sure what's known here. But so yeah, this is from a book on computer algebra. That there's a lot of work that has gone over finite fields factorization. So let's talk about multivariate case. So in the multivariate case, so like Abhishek said, so the question of representation is also important. So if one way is you can just be given the coefficients of all your monomials, and then you're asked to give a factorization. But another kind of question is, if you're told that your polynomial f has a small representation of some form script C. So this can be a small circuit for f or something of that sort. And you want to know, do its irreducible factors also have small representations, reasonably small representations of the same form? So for in the dense representation, which is when you're just writing polynomials as monomials, this is clear. Any polynomial's factors will also have a small representation in that, but it's not clear in many other succinct forms. So that's just the existence question. Do irreducible factors even have a small representation in the sort of form you care about? And then there's a stronger question of, can we efficiently find such a small representation? That is, let's say you're given a small algebraic circuit for your polynomial. Can you find small algebraic circuits for its factors? And so in this, there's been a long line of work. And so some of the names here are Kaltofen, Fraser, von Zurgatzen. And one of the landmark results here was that they gave an efficient randomized algorithm which takes the multivariate polynomial, which takes an arithmetic circuit for a multivariate polynomial, and then spits out small circuits for all of its irreducible factors. So now what I want to do is just sort of take a small example and go over the sort of ideas that one can use to factorize this. So let's say this is the polynomial, multivariate polynomial, and right now it's just bivariate, and we want to try and factorize this. So what do we know till now? So we saw that, okay, somehow univariate factorization we know how to do. And right now that's essentially the thing we know how to do. So we are going to try and make this univariate somehow. And how can I make this univariate? When one way is you just set one variable to be some value. Let's say you say, okay, I'm going to set x to be equal to 1. So now suppose you set x to be equal to 1, and the new polynomial that you get, it turns out to be irreducible. So we know how to factorize univariate polynomials. If this univariate thing turns out to be irreducible, what can we say about the original polynomial that we started off with? It has to be irreducible, because if it had a factorization, then even when you set some variable x to some value, that gives you a factorization even in the univariate world. So the counter first is.
What is the rule that one of the factors can only x?
Yeah, so there's always going to be some technicalities of ensuring that your polynomial has a certain structure so that some degenerate thing doesn't happen. I'll mostly be glossing over many of those details, but yeah. Okay, so let's say this was a polynomial, and I just arbitrarily, so at this point it's quite arbitrary that I chose x is equal to 1 to be the thing I'm plugging in. But there are some conditions you would want for what you are plugging in, so that things don't break down completely when you go to the univariate world. And what does it mean for things to break down? These are all things that have to be formalized. We'll briefly go over those things towards the end. So now, if your polynomial f of x comma y was some g of x comma y into h of x comma y, then f of 1 comma y is g of 1 comma y into h of 1 comma y. And let's say g was not just something completely in x variable. Both of these had y variables and things like that. So now we are going to use univariate factorization on this f of 1 comma y. So this, we use some off-the-shelf algorithm, and you get this to be your factorization. Okay. So maybe what we can say is that initially there was some factorization. So at this point, the only access we had for the original polynomial was, like, let's say it's complete monomial form, or let's say some circuit that computing it. And now we came down to this univariate world, and now we can see that this univariate thing has two factors. I'm making a simplification by saying that, okay, maybe one of these factors corresponded exactly to a multivariate factor, and the other again corresponded exactly to the rest of the polynomial. And in this case, it turns out to be true, but this is just a simple case for the ease of analysis. So let's say these are the univariate parts you get from your multivariate factors. So this is a factorization of your polynomial modulo x minus 1. What does that mean? In a world where x is just plugged in to be 1, this is actually a correct factorization for f of x comma y. Equivalently, again, for the ease of analysis, I can say that this is a factorization of f of x plus 1 comma y modulo x. I mean, instead of x and x minus 1, I have x plus 1 and x. So all this is saying is you take your original polynomial, and instead of x, you plug in x plus 1. Now, if you plug in 0 here, it is the same as having plugged in 1 in the earlier case. So I'm going to work with this shifted polynomial. And now I'm saying this univariate factorization that I have, it's sort of like an approximate factorization, in the sense, if you're happy with the factorization that's correct modulo x, then this is correct. Now, so this is just what I said, that we'll redefine our f to be with the shifted x. Now the idea here is, can we sort of improve this algorithm to be correct modulo x square? So right now the factorization is correct modulo x. We want to improve it to be correct modulo x square. So this is the idea. And so there's a tool in this literature which is called tensor lifting, and so I'm going to flash what this is, and I'll just let you have a look at it for a second. So let's just go over this. What it's saying is, if you have some f, and f is going to be monic, these are like, I'm slowly introducing all these conditions that you need so that things don't break down. All monic just means that the highest degree like term, so let's say this was some polynomial in x and y, right? So let's say it's y to the power d plus blah blah blah. So, and you're given that it is a factorization gh, and you have some factorization for it modulo x to the I. So f is some g prime h prime, and this is a correct factorization barring higher degree x terms. And you know that g and h are co-prime, again modulo x to the I. So ag plus bh is equal to 1. This is sort of this Bezout sort of statement for saying when are two things co-prime. And you know that this g prime and h prime, they are actually, like, if you take your original factorization and drop down to this x to the I word, they are actually the same things as what you currently have, this g prime and h prime. So if you have this approximate factorization modulo x to the I, then what tensor lifting gives us is an easy way to compute a better factorization. That is, you will now be correct modulo x to the power 2i. So your accuracy with respect to x degree doubles. And tensor lifting, so right now I'm just giving you what the statement is, how exactly you go from compute this lift. I'm not going to go over that. But the point is, this is easy to do. So there are a few different versions of this. There's versions of this where you do not have this monic guarantee. So then you don't quite get this sort of uniqueness. So what this is saying is that when you compute this lift, this is actually going to correspond to your original factors. But that need not be the case if you don't have f being monic and so on. So there'll be some slight technicalities that one might have to deal with. But the main idea of tensor lifting is, if g prime h prime is a good factorization up to x degree I terms, then g double prime h double prime is a good factorization up to x degree 2i terms. And so right now I just want to quickly show how do I stop? So in fact, these things can be easily implemented in, let's say, things like, oh, I haven't. I have. Oh, okay. So you can in fact implement these things in like, oh. What? It's fine. Yeah. Okay. So this is the way I came up with our polynomial in the slides. So this is just setting up some polynomial rings, and this is a polynomial that we want to factorize. And then I said, okay, let's do this shift of setting x to be x plus 1, and I go to the univariate setting, and then I factorize it, and I compute these Bezout coefficients and so on. And now this is actually, so this is the tensor lifting. This is the exact code for tensor lifting. There is a way of going from your current g and h to the next g and h, and these are some simple operations. And it turns out that, so when you do this, you start off with the univariate thing. You actually start to accumulate some garbage terms. But tensor lifting is sort of giving you a guarantee that if you ignore those higher degree terms, then you're actually computing a correct factorization. So you can do this, repeat this for a few steps, and you can show that you actually don't need to go too far, because the degree accuracy doubles in every step. So if your original polynomial was of degree d, then you only have to do it for some log d sort of steps to get enough accuracy. And then once you are done computing this, so even here, if we go scroll down to the end, oh, this is actually pulling down quite. Yeah, so here in the end, you will see that there is a small there's something that sort of might make sense for what we really care about. And it turns out that if you take the G finite to be basically you're throwing off higher degree terms in both your G and H, and then if you check what is if you just multiply them, you'll see that it's the same as what you started off with. So the algorithm is actually quite easy to implement and it works out fine. In this example, this is a really simplified example. So yeah, so we were here. Oh, it's not yet loaded. And so yeah, at each step we are doubling the x degree accuracy of our factorization. So if you started off with degree d thing, then in order log the iterations, you can sort of retrieve the factorization. And if things were, I've written if there are extra terms, we can throw them away. I'll come to that again. But if you turned out to be really lucky, and when you drop down to your univariate world, you somehow happen to take exactly the things that corresponded to a factor that you want, then you can do this throwing away. So for example, in the case that we had, once you go from multivariate to univariate, the irreducible factors here exactly corresponded to the irreducible factors in the original multivariate world. But it's possible that once you go from multivariate to univariate, when you plug in something, an irreducible polynomial factorizes into a few things. So then you need to start thinking about how to deal with those cases. But overall, the typical steps in a multivariate factorization algorithm are you do some pre-processing. By pre-processing, I mean you ensure that your polynomial is monic and so on. There'll be a separate slide just for going over these things. And then you drop down to the univariate world by setting all except one variable to some field constants. It's important what those field constants are so that you don't break things when you go into the univariate world. And then you do univariate factorization. And then you do this Hensel lifting to start lifting to get better and better approximate factorizations. And then you finally do some cleanup and reconstruct the original factors. So let's look at the pre-processing step. So one thing we want to ensure is that f should be monic in some variable. For example, the polynomial example we saw, it had just a y to the d in I think y square or y to the y cube or something like that. So it's not 3x square y cube or something, because if you plugged in x to be 0, then that term disappears and you start to lose information. So we don't want to do that. So we want f to be monic in some variable. You want to ensure that when you plug in 0 for some variables, the factors shouldn't mix up. What does that mean? So let's say this is some polynomial you started off with, and you can sort of verify that in let's say a rational number or something, these are irreducible. And if you plug in x to be equal to 1, so I said plugging in 0, but again we can do this shift of x going to x plus 1 and so on. If you plug in x to be 1, then the first factor becomes y plus 1 whole square. The second factor becomes y plus 1 into y plus 2. So now y plus 1 is a common factor here. And we don't have that original factorization. All we had was that thing opened out. But once you look at the factorization in the univariate world, you are seeing some y plus 1 factors with some multiplicity. You don't quite know where did these things come from. So we want to ensure somehow that when you go to the univariate world, the corresponding factors don't start mixing up. They don't collide with each other. So we do not want this to happen. And it turns out that such conditions can be captured by saying that some polynomial that involves your initial f and so on, it needs to be non-zero. So all I'm saying is that you want to do some shifts. Let's say here we said we shifted x by 1, we did x plus 1. So you might want to do some such shift, and what those shifts are can be captured by those shifts being a non-zero of some polynomials. Those polynomials turn out to be these things called resultants or discriminants. Again, won't go into details. And it has a random shift work to ensure these conditions. And then there's the reconstruction step. So I see that I'm almost out of time. I'll take a couple of minutes. So there's the reconstruction step where I said when things are all nice, then you can maybe just throw out the higher degree garbage stuff and then you'll be fine. But in general, you might have to do some step where you solve a linear system to reconstruct a factor, which is also not hard. And the intuition for why something like this might happen is, as I said earlier, it's possible that you started off with some factorization of this form. Let's say these are irreducible in the multivariate world. But once you went into the univariate world, the G might have decomposed into two irreducible factors, G1 and G2, and H might have stayed the same. And when you now started off with this Hensel lifting procedure, it's possible that you ended up choosing G1 to be a block and the rest of the block to be the rest of the factors. And so once you lift this, G1 of 1 comma y doesn't really correspond to any irreducible factor of your original polynomial. So how do you incorporate that remaining block? It turns out to be possible by solving some linear system. And now I just want to see where we use randomness in this procedure. So, okay, there's a lot of hand waving here. The algorithm template that we saw, it turns out to be efficient. But it's a randomized algorithm because the shifts that we did to ensure that things don't break, those we did randomly. So ensuring non-zeroness for certain polynomials. So for monicness, you ensure that some highest degree homogeneous component is non-zero. Then for this GCD, so G and H not mixing up even when you go to the univariate world. This was some resultant condition. I won't tell you what the resultant is, but it captures somehow the GCD of G and H being equal to 1. And random points from a not too large set suffice when you want to ensure that these conditions are true. And the idea here to de-randomize this is if we can deterministically find such points such that you can ensure these conditions to be true, then you can get non-trivial deterministic algorithms for factorizing multivariate polynomials. There's a star there because this is all a simplification, but the main idea is this, that there are some points where you are randomly doing some things and that we know how to do efficiently. So there's things like, even to get a non-zero of a polynomial, there's things like Schwarzschild lemma, which will tell you how to do that efficiently, randomly. But if you can do that deterministically somehow, then you can do the whole procedure deterministically. That's something one can hope for. And our work here is for, so because there was a star there, there are still a lot of things that one needs to take care of. And what we were able to do, so this is with Mrinal and Ramanathan. So if your F was given as a low depth circuit, so circuits are these directed acyclic graphs where, like, instead of Boolean circuits where you have OR and AND gates, you have addition and multiplication gates. And if it's a low depth circuit, then we are able to output a list of all low degree irreducible factors. Low degree, let's just say some constant degree, all degree 100 factors or something like that. I can print those out deterministically in sub-exponential time. And if moreover F was sparse, sparse just means that the number of monomials, which could originally have been like n plus d choose d, which could have been like n to the d, something huge. If you are given some bound on how many monomials there are, and if it's something manageable, then we can output a list of all low degree irreducible factors of F deterministically in quasi-polynomial time. And now these, like, out of context, these bounds seem like maybe not that impressive, that it's sub-exponential or quasi-polynomial. But in this field, so till a recent work of Pope's, we did not even know how to do divisibility testing for this problem, which is you're given a sparse polynomial and let's say some constant degree polynomial. You just want to check if this constant degree polynomial divides the sparse polynomial. These are multivariate polynomials. We did not know how to do this till 2015. So now we can, so we knew at that point, folks showed us how to do this problem in quasi-polynomial time. Using similar ideas, we can, in fact, even using this algorithm of divisibility testing, we can print out all low degree factors in quasi-polynomial time, and for low depth circuits in sub-exponential time. And along the same vein of trying to connect de-randomization of polynomial factorization to de-randomization of this polynomial identity testing, which is finding non-zero for some polynomial. There was a work by Koparthi, Saraf, and Spielka, where they did reduce factorization to polynomial identity testing, but that wasn't fine-grained enough, in the sense, even if you want to do polynomial factorization for simple classes like sparse polynomials or low depth, the polynomial identity test that turned up in that question turned out to be for harder classes like ABPs or something. So that wasn't quite useful. Like, there's been a lot of progress in de-randomizing polynomial identity testing for simple classes, but that's somehow not useful through the works of KSS and so on, because there you require PIT for harder classes. So in our work, we have somehow shown that at least if you just want to print out low degree factors, then you can do this deterministically. And the way you do this is just pay attention to the resultant and so on, and see that if your original polynomial was simple, then the resultant is also simple enough that you can do this polynomial identity testing relatively efficiently. So I'm out of my time. Any questions? I'll be happy to take more detailed questions after the. Okay. Thank you.